Hello everyone. Today we are going to discuss the important concept of periodic table, that is alkali and alkaline earth elements. Alkali and alkaline earth elements play a very important role to deciding the different properties of the different elements. Alkali elements, the primitive element hydrogen that were already discussed, and the other element are lithium, sodium, potassium, rubidium, cesium, and francium. And alkaline earth elements are beryllium, magnesium, calcium, strontium, barium, and radium. In the initial version, we are going to discuss the different important periodic properties, periodic trend of these alkali elements. The atomic number of lithium is 3 and consecutively increased by 8, 11, 8, that is sodium has 81, potassium has 19, and rubidium has 36 and cesium has 55. As a trend, melting point of alkali earth element are reduced from top to bottom, that is from lithium to cesium. Again, in the case of boiling point also, they are increasing in a descending order. Heat of formation is larger in the case of lithium, while it is lower in the case of cesium. That is, the size is play a very important role deciding the heat of formation. Heat of formation, that means lithium can form a bond with the other elements. Then atomic radius. As you know that as the go from upper to down, the atomic size of sodium to cesium has been increases sequentially. Therefore, its atomic radius is also increases sequentially. Then ionic radius. Generally, lithium or alkali elements are found in +1 oxidation state. That means Li plus, Ni plus, K plus, Rb plus, and Cs plus. Ionic radius has been increases from lithium to cesium by losing of one electron. Then ionization potential. Ionization potential is the amount of energy that required to remove the outermost electron from the element. And the first ion, if the first electron is ejected out, then it is called as first ionization energy. Second electron, then it is called as second ionization. But in the case of alkali earth elements, it has the general configuration S1. That means 1 ampere electron is present in S1 orbital and it is easy to eject out. Therefore, the lithium has generally found, not only lithium, but all the alkali elements are found in +1 oxidation state. The amount of energy required to remove the outermost electron from lithium is maximum because the lithium has smaller in size. Therefore, the distance of outer electron from the nucleus is very much less as compared to sodium, potassium, rubidium, and cesium. And therefore, as the size of atom increases, the hold of outermost electron is get reduced. Therefore, the amount of energy required to remove the outermost electron is less as the size increases. And therefore, the same trend is observed in the case of these lithium to cesium. Then electron affinity. Electron affinity is the attracting power of electron. That means it has the affinity of electrons and it is not so fastly reduced but slightly reduced from lithium to cesium. Electron affinity, it shows 59 kilojoule per mole in the case of lithium, while in the case of sodium it is 52 kilojoule per mole, and in the case of last cesium it goes down up to 45 kilojoule per mole. That clearly indicates the descending trend, although it has a descending trend, but the rate has been slowed down. Again, the next important trend periodic property is the dissociation energy. Again, it is a resemblance with the ionization potential. As the size increases, dissociation energy decreases. Why? Because again it is similar with the ionization potential, that means amount of energy required to dissociate. That is, as the size increases, the hold of outermost electron is slightly get reduced. Hold of, and therefore the dissociation energy decreases from lithium to cesium. Then again the Pauling electronegativity. There are the two types of electronegativity, Pauling electronegativity and ALKALI electronegativity. Pauling electronegativity, it is slightly decreased from lithium to cesium. In the periodic table, it is from top to bottom, generally the electronegativity get reduced. And the same trend has been found in the case of Pauling electronegativity as well as in the case of ALKALI electronegativity. There are the two different formulas investigated by Pauling and Allen, and on the basis of that, they are calculating the electronegativity, and therefore they have slight difference in their values. Then the important test of alkali and alkaline earth elements, that is, they have shows the flame test. The alkali earth element can be easily detected by the flame test, and that's why this flame test is so much important for it. The flame test color appearance, that is based on the principle of emission and absorption wavelength in nanometer. That means I have given you the nature of color change in the flame, while whenever these lithium is put in a flame, it shows the crimson in color, while sodium shows yellow color, potassium shows violet color, rubidium shows red violet, and cesium shows blue in color, on the basis of their different wavelengths. Lithium shows the maximum wavelength at 670, sodium shows at 589, while potassium shows 766, rubidium shows 780, and cesium shows at 455. So this is all about the periodic trend of alkali elements. Now the important property we are going to discuss, that is alkali and alkaline earth metals solution in non-aqueous media. An ionic non-aqueous solvent is a solvent other than the water that is not an organic compound. Common example of is the liquid ammonia, liquid sulfur dioxide, sulfuryl chloride, fluoride, phosphoride chloride, dinitrogen tetroxide, antimony trichloride, bromine pentafluoride, hydrogen fluoride, pure sulfuric acid, and other ionic acids. These solvents are used in a chemical research and industries for reaction that cannot occur in aqueous solutions or require a special environment. Alkali and alkaline earth metals solutions in the non-aqueous media. Acid-base reaction in non-aqueous solvents are typically, as explained before, are typically described by the means of solvent system definition. Although the Lagrange-Bronsted-Lowry theory may be applied there for the protic solvents, which possess hydrogen that can be dissociated. According to the solvent system definition, acids are the compounds that increase the concentration of solvonium ions, and bases are the compound that result in increase of the solvated ions, where solvonium and solvate are the ion found in the pure solvent in equilibrium with its neutral solution. Protic solvent, I will give the example of protic and aprotic solvents. Protic solvent, ammonia, which when the two moles of ammonia get dissociate unequally. That means one ammonia molecule get the one extra electron from another adjacent ammonia molecule, and one ammonia it loses its hydrogen, and therefore the formation of NH4 plus and NH4 minus. And see the beauty of the chemistry. That is, the ammonia has been in a different form. One is in a NH4 plus in a plus form, while the other in a NH2 minus. It is in a amide form. That means, as you learned in the case of Gichi-Webern reaction, the role of amide as a nucleophile. And that we have to learn in organic chemistry. Then again, in a second reaction, when hydrogen fluoride, it get dissociate, 3 molecule of hydrogen fluoride get dissociate. They are also again dissociate unequally. They are dissociate into H2F plus. And again, then HF2 minus. There is the unequal distribution of hydrogen again here. In the third molecule, we are taking into consideration, that is sulfuric acid. When the 2 molecules of sulfuric acid get dissociate, they again dissociate unequally. H3SO4 plus and HSO4 minus. Then again, we are taken some examples of aprotic solvents for autodissociation. First example is N2O4. It gets dissociate into NO plus nitrosonium ion, while NO3 minus, that is nitrate. SbCl3 dissociate into SbCl2 plus and SbCl4 minus. POCl3 get dissociated into POCl2 and POCl4. Thus, NaNH2 is a base and NH4Cl is an acid in liquid ammonia. And they react, producing the salt and the solvents. NaNH2 plus NH4Cl, it gives 2 molecule of NH3 plus NaCl, or for aprotic examples. NaNO3 plus NOCl, again it gives N2O4, the synthetic method of N2O4 plus NaCl. And now we goes toward the important topic of alkali elements, that is the role of crown ether in the extraction of alkali and alkaline earth elements. Generally, crown ethers are of diethyl ether type of, or it is a derivative of 1,2-diol. When the 3 molecule of 1,2-diol are combined with each other, they can form a 18 crown 6. That means, when by the naming, it has been nomenclature, it is also known as 18 crown 6 on the basis of their number of atoms attached to it. That means doing the summation of all the carbon atoms and oxygen, we are getting the number 18. Crown, that is crown-like shape, and 6 means the number of oxygen. On the basis of that, they are given the nomenclature as 18 crown 6. While in the case of second, there are the 5 oxygens are there and total atoms are 15, therefore named as 15 crown 5. In the third example, 4 oxygens are there while the total number of atoms are 12, therefore 12 crown 4. These compounds are called as crown ethers because their molecules have a crown-like shape. The bracket number represent the ring size and the terminal numbers give the number of oxygens. The oxygen are usually separated by 2 carbons. See, the important of these crown ether are used as the intercalation compounds. Generally, they have inside the space of crown ether, there is some cavities is there, and beyond it can be used as an intercalation compound, means the trapping of different molecules, with the radius of these internal cavity as per the cavity diameter. Crown ethers have the unique property of forming complexes with positive ions Na plus and K plus, with the positive ion fit within the microcyclic ring selectively depend on the size. For example, 18 crown 6 binds potassium more tightly than it does smaller Na plus. Na plus get loose through that 18 crown 6, and therefore it can be eliminated out as like a molecular sieve. Or CS is a larger, CGM is a larger as compared to the cavity of the 18 crown 6. And therefore, by using the 18 crown 6, potassium, we can able to separate the potassium specifically from other alkali elements. And that is the main important application of a crown ether, to separate out as a molecular sieve. It can be also used as a molecular sieve, and it has to play a very important role in this way. Now, similar to the crown ether, some krypton compounds are there. More than one cycle is there. If it is bonded with the two cycles or two different heteroatoms. In the first example, in a crown ether, we have learned that there is only one heteroatom, that is oxygen. But in this case, two heteroatoms are there, one is oxygen and second is nitrogen. Again, these are the bicyclic ring. That means two cycles are there. That is, on the basis of their cycle, they are named 211. That means 2 is the number of nitrogens which are present at the terminal position, while 1 and 1 is the ring size. While in the case of these, 3, 2, 2, these are the examples of krypton. And last, but how the crown ether play a very important role in the case of phase transfer catalysis. By making the cation large 18 crown 6 destabilize solid or aqueous KMnO4, allowing the salt to dissolve hydrocarbons, as shown by the purple ring. Then, how the function of 18 crown 6 play a very important role in the separation of compounds. For example, this organic solvent I shown above, and below is the H2O, water solvents. Whenever the crown ether play a very important role to entraft some molecule in the organic phase as well as in aqueous phase, and to do the reaction in organic as well as in aqueous phase. And this is a very important part which play a role in this way. I have taken the example of 18 crown 6 when entrapping of NH4 plus. This NH4 plus get entrapped inside the cavity in this way. The F minus ion below is ready to react because the K plus ions is sequentially by the crown ether. That means K plus ion has a suitable radius along with the cavity of the 18 crown 6, and therefore these K plus get entrapped inside the cavities of the 18 crown 6, and F minus get separate out. F minus get along with that emulsion and to it react. It is available for reaction now. Without the crown ether, the solubility of Kf in benzene is not calculated. Then the important role of organometallic compounds, these alkali and alkaline earth elements, is they play a very important role in organometallic chemistry. In the primitive era, the organometallic chemistry, these lithium compound, magnesium compound, and beryllium compounds are considered as organometallic compounds. The important compound among them is the Grignard reagent. Sir, Grignard in 1902 has been investigated the one important catalyst, that is Grignard reagent, which changed the chemistry so far. And on the basis of this, these Grignard reagent, initially, it is considered as organometallic compounds. It has some important properties. Due to its large difference in electronegativity between the carbon atom and the lithium atom, the carbon-lithium bond is highly ionic. The extremely polar nature of carbon-lithium bond makes organolithium reagents good nucleophile and strong bases. For the organic synthesis, many organolithium reagents are commercially available in the solution form. And these reagents are highly reactive and sometimes pyrophoric. There, in the case of Grignard reagent, organolithium compounds are used as a very strong base. They can react with any compound that has the hydrogen attached to the electronegative atoms such as oxygen, nitrogen, and sulfur. We can understand how these reactions occur if we represent the Grignard reagent and the organolithium compound in the following ways. I have shown you the simple reaction of organometallic compound of the Grignard reagent with the water. Then what happens? This RMgX get abstract the proton from the H2 and it dissociate out MgOHX as in the solution media. But in the case of in the second case, when these Grignard reagents react with alcohol, then again the same role Grignard reagent has been performed. It gives the R, that means substituent group, and it abstracts the hydrogen, acidic hydrogen from alcohol. Again, it will form the weaker acid. Initially, this RMgX is act as a stronger base because it is as a nucleophile. And in the second, whenever it form a compound, it will become a weaker acid as per the HSAB principle. The Grignard reagent and organ lithium compound remove protons that much less acidic and those of water and alcohols. Grignard reagent react with terminal hydrogen of one alkyne by an acid-base reaction, and this is a useful method for preparation of alkyl magnesium halides and alkyl lithium. And last, but very much important, is the flame test. These alkali elements are show a very different electronic transition. That means different colors for the alkali elements. For the identification of alkali metal and their compounds, electronic transition occur within the metal atom, and ions form in the flames with energies that fall in the visible part of the spectrum, give the characteristic color to the flame. Lithium shows crimson color, sodium yellow, potassium red to violet, rubidium violet, and cesium blue. Again, these NaCl salt and CSCl salt, they have the different structures, and therefore they play a very important role in a structural chemistry or solid chemistry also. So I show some primitive examples of it. For example, rock salt structure, in which the NaCl molecule show a rock salt structure, while CSCl shows the CSCl type of structure. They have the different crystal lattice. They have the crystal different morphology, and on the basis of that, they are easily separated out. Then the last year Nobel laureate is the invention of lithium battery. And dear friends, it is very important to know basics about that lithium battery. The very negative standard potential and low molar mass of lithium make it an ideal anode material for the batteries. These batteries have relatively high specific energy because lithium metal compounds containing lithium are light in comparison with some other materials used in batteries, such as lead, zinc. Lithium batteries are common, but there are many types based different lithium compounds and reactions. And the lithium rechargeable battery used in portable computers, phones, mainly used in all the sophisticated instruments. As a cathode within the lithium graphite, lithium ion are produced at anode during the battery discharge. To maintain the charge balance, cobalt in plus 4 oxidation state is reduced to cobalt 3 in the form of LiCoO2. At cathode, the reactions occurring during the battery discharge are given below. Lithium LiCoO2 in a 4 oxidation state get reduced into CO in plus 3 oxidation state. While at anode, these C6Li get bifurcated in 6 carbon, get in the form of graphite and lithium, which is in a solution form. The battery is rechargeable because both the cathode and the anode can act as a host for the lithium Li plus ions, which can move back and forth between them. When charging and discharging, there are many other lithium batteries using different electrode material, mainly D metal compounds, that takes part in the redox reaction in the similar way to the cobalt. The latest generation of electric cars uses lithium battery technology rather than the lead acid cells. Another popular lithium battery uses thionyl chloride, SOCl2. This system produces a light, high voltage cell with stable energy output, and the overall reaction of the battery is lithium with thionyl chloride. It will give LiCl plus sulfur has been eliminated out and SO2 sulfur dioxide in a liquid form. The battery requires no additional solvent as both SOCl2 and SO2 are liquid at the internal battery pressure. This battery is not rechargeable as both sulfur and LiCl are precipitated. It is used in a military application and spacecraft. Another battery system is based on the reduction of SO2. And this is all much information related with the lithium battery, and it is a very important recently information we must know. So alkaline earth element again show such type of crystallographic structure For example, I have taken the example crystallographic structure of CaF2, SrF2, BaF2, and SrCl2. Again, alkaline earth element, they are containing beryllium, magnesium, calcium, strontium, barium, and radium. And these compounds are shows the fluoride type of structure, and I shown here. This is all the information related with the alkali and alkaline earth elements. If you have any query, please you can send me your suggestions regarding with the video. Okay, thank you.